Today my topic is under operating systems. What are the scheduling algorithms that we'll discuss one by one. So in the previous class we have discussed about the different what is the algorithms of this CPU scheduling, and what are the programs available in the OS. These are the programs available in the OS. How to manipulate this processes. So the types of CPU scheduling algorithms there are mainly 6 types of scheduling algorithms. The first come first service, and shortest job first, priority based scheduling, shortest remaining time, round robin, multi-level queue scheduling. These are the programs, rather you can say the OS, to handle the CPU, which process to be executed first, and it will be, these programs will decide as per the requirement of the user. So let us see one by one. So the first scheduling algorithm is the first come first serve. That is first come first serve means, as I explained in the previous class, this is a program we write, and after compilation we'll be loading into the hard disk. This is a program saved in the hard disk. So when you want to execute this program again it will brought back to the RAM. That is your ready queue. From ready queue, it will be sent to the CPU. So what we are discussing, CPU. Then the CPU, there is one circuit, ALU, arithmetic logic unit circuits are there. These circuits only execute the program, execute the instructions one by one. This is the queue. What is there? So these algorithms available in the OS, or rather you can say the programs available in the OS. These programs will manipulate the complete process management. This is nothing but process management is done by the CPU scheduling programs. And we'll see one by one. This is the first come first serve. Is a full form of FCFS. So in this one, it is the easiest and most simple CPU scheduling algorithm. In this type of algorithm, the process which requests the CPU gets the CPU allocation first. So as we are discussing, this is your program the RAM, and this program instructions are coming to CPU for execution. So these are the instructions 1, 2, 3, 4, 5. So whichever the instruction in the first comes to your CPU, the CPU is allocated by OS, and this program is allocating this user program to execute. So whichever is the first instruction first, second instruction, this after completion of this one, second instruction will come for CPU for execution. This is what is the first come first serve basis. So which instruction comes first, irrespective of the CPU time, CPU burst time and all, and this will be executed till end, terminated. So in this type of algorithm, the process which requests the CPU gets the CPU allocation burst first. The scheduling method can be made and named just like managed by FIFO, first in first out. The first instruction will come for the CPU, so it will execute out. Next instruction will come from the RAM to CPU, that will be executed and out. The out means terminated from the CPU. So as the processes enter the ready queue, that is ready queue is nothing but your RAM. It's a PCB process, PCB, as I explained. Whenever the process enters in the CPU, automatically process control board is tracking up this process, when it entered, when it is going out, what is our PCB program counter, address, everything is linked to this tail of the queue. This is PCB is linked with the tail of the queue, that's FIFO. So when CPU becomes free, it should be assigned to the process. So process at the beginning of the queue. So what we're discussing. So if you look at this CPU scheduling algorithm, so just you see, this is a processes. Processes means the instructions are coming for the execution. This is process 0, process 1, process 2, process 3, and arrival time in the CPU, the arrival time in the RAM. This is 0, 1, 2, 3. This is, you can say, assume that milliseconds or microseconds or nanoseconds. It depends. So this is an example what is going on in the CPU. So next, execution time. So how much time how much time it takes to execute process 0, and how much time it takes. That means how much time the CPU spend with the process 0. 5 milliseconds time, 3 milliseconds, 8 milliseconds, 6 milliseconds. Process 3, it takes 6 milliseconds to execute. That is, rather you can say, CPU spends 6 milliseconds with the P3 for execution. So this is service time. So if you look at this one, initially service time is 0. Next P1 will start 5. That is 5. So you can keep on accumulate. So you will get 16. So if you this is the GNAT chart. We will draw the GNAT chart from the this given time. This is the time will be given in the exam. So we have to draw this one. So P0 starting at 0, arrival time 0, and how much time it takes? Execution time 5 milliseconds. So 5. Next P1 will come for the execution to CPU. So it takes 3 milliseconds. There are then 5 plus 3, 8. So P1 will be completed by 8. After P1, P2 will be entered. P2 time is 2. Time is 8. So 8 plus 8, 16. 8 plus 8 takes 16. And P3, after P3 will come. P3 takes 6 milliseconds. So 16 plus 6, 22. So by 22, the job is completed. This is program will be executed. 22 milliseconds. It takes 22 milliseconds to execute the complete program, process by process, like this. The first come first service this is the first come first service. So now we will do some calculations. So if we look at this wait time of each process as follows. So as we have given the previous class, we have given some formulas. That is wait time equal to service time minus arrival time. What is the service time? This is service time. This is service time. So the process P0 waiting time equal to that is service time minus arrival time. This is arrival time. So 0 minus 0, it is 0. So straight away it is entering into the CPU for execution. It is not waiting in the queue. So that is called service time. And so now we'll see look at the P1. How much time P1 take? What is the waiting time for the P1? So P1 time is equal to P1 wait time equal to service time minus arrival time. This is service time for the P1. Service time 5. So we'll see one by one. Service time of P1. The 5 minus 1, 4, and for waiting time for the P2, 8 minus 2, 6, and for P3, 16 minus 3, 13. So once you got these values, so average wait time equal to adding all these things, that is, so 0 plus 4 plus 6 plus 13, and by average time we have to divided by 4, we will get 5.76 is the average waiting time for each process. Characteristics of FCFS method. It offers non-preemptive and preemptive scheduling algorithm. Jobs are always executed on first come first serve basis. It is easy to implement and use. it. However, this method is poor in performance and general wait time is quite high. Why? Because as we have seen, these are the programs when coming for CPU for execution. So first come first serve means first will come for the execution. So it may be having the more time for execution, maybe 10 milliseconds or 20 milliseconds. Till its completion, 10 milliseconds, second process cannot enter. That is called first come first serve. Because because of this reason only, the waiting time is more for the processes. Yeah. So because of this reason, this is advantage, disadvantage of the FCFS, first come first serve. So we will see another algorithm or another CPU scheduling algorithm. This is shortest job first. Shortest job first means out of this all this this is a program. This is a program what you write, and when this program coming for execution, that is called process. This will become process. Process means program under execution is called process. So when this is out of this all these instructions, which instruction takes less time, very less time, that will be sent first, because it may be 100 or maybe 100, maybe 200 line. That each line is an instruction. So if this takes less time, that will be sent first. That is the beauty of this algorithm. So in this one, waiting time may be less, will decrease. That's one what we go for. This is also known as shortest job first, or as JF. This is non-preemptive scheduling algorithm. So best approach to minimize wait time. Easy to implement in batch systems where required CPU time is known in advance. So CPU time means how much time that instruction will spend with the CPU. That is called CPU time. So once we know which instruction is having the very less time, that is called shortest job, that will be given preference first. So that because of that one, waiting time will decrease. So this is best approach to minimize waiting time. This is the best approach for the waiting time, because if suppose one instruction has gone to CPU for execution, if that instruction CPU burst time is more, other instructions will have to wait till that instruction is completed. That execution is completed. So the waiting time, as you see, look at this one, waiting time is increasing. So if you use this one, shortest job first, the waiting time will be decreased. That is the only advantage of this one. Easy to implement in batch systems where required CPU time is known in advance, because once you know the CPU burst time in advance, then only we can go for this one. So impossible to implement in interactive systems where required CPU time is not known. If CPU time is not known, which instruction takes how much time, that we must know advance. If you don't know that one, then we cannot go for this shortage of course. That is only difficult. So the processor should know the advance how much time each process will take. That's the important one in this algorithm. So this is example of a shortage job first. So as we have seen the previous slides, first come first serve. So this is here also P0, P1, P2, P3. They are the processes, and these are the arrival times in the CPU on the ready queue. And this is the execution time. That is, execution time is nothing but CPU burst time. This is execution time. This is the service time. How much time service? Initially 0, 0 plus 5, 5 plus 8, 5 plus 8. So these are your service time. If you look at this one, this is execution time, service time. Now we'll write the Gantt chart. The Gantt chart, how much time each process will take. This is initially 3. So service time 3, and 3 plus 5, 8. So like this, we will get the Gantt chart. So we will calculate the average waiting time for each individual process. As you know, the formula, waiting time equal to service time minus arrival time. So P0 0 minus 0 0, P1 0 5 minus 1 4, and P2 14 minus 2 12, P3 8 minus 3 5. Because shortest job, which is the shortest job, that will be set first. So once you add all these things, dividing by 4, you will get 5.25. In the earlier FCFS, that is the average waiting time is 5.75. Now average waiting time has been brought down to 5.25. This method is mostly applied in each batch environment, where short jobs are required to be given preference. This is not an ideal method. to implement it is in a shared system where the required CPU time is unknown. If you don't know how much time taken by the process to complete its instruction, I mean its job with the CPU, then we cannot go for this shortage of us. So this is very drawback of this job shortage of us. So next, so priority based scheduling. This is another CPU scheduling algorithm. In this priority based scheduling algorithm, priority scheduling is non-preemptive, and one of the most common scheduling algorithm in the batch systems. Each process is assigned a priority. Process with high priority is to be given executed first, and so on. So as you know, this is instructions program. You're right. So we know these are the each instruction is a process only. So if this process if this process is not executed, I mean its output may be helpful for the. So in this priority based scheduling algorithm, priority scheduling is non-preemptive algorithm, and one of the most common scheduling algorithm is in the batch systems. Each process is assigned a priority. Process with the higher priority is to be executed first, and so on. The processes with the same priority are executed. That means if two processes having the same priority, and the order should begin. That is first come first serve. Again, the first come first serve basis will be taken into consideration. So priority can be decided based on the memory requirement, time requirement, and other resources. So one should have the doubt. So how priority decided? How priority will be given for the instructions? So what are the instructions? They were instructions in the program. So it will be decided the priority that on based of two conditions. One is the requirement of, that is time requirement, and memory requirement. If memory is more, it is occupying more memory, it should be given priority. And at the time, if the instruction is executing very fast and time is very less, then the priority will be given on the basis of these two conditions. One is memory, and another is time requirement, time or how much time it takes to execute. So this is a example for the priority scheduling algorithm. So one is the process, as it is earlier you have seen this first come first serve and shortage of us, and this also similar to that one. In this one, process P0, P1, P2, P3, this arrival time in the RAM, but that is brought from the hard disk to RAM when the instructions are coming to RAM, and this is the execution time, and priority will decide as per the on the conditions whether how much time it takes to execute, and as well that one high priority. This is, as you look at this one, 8 is given the high priority, and like this is the priority is given. So 5 and 8 are both are given the same priority. In that case, again first come first serve. So this is a thing. So if you look at this, if you draw the priority GNAT chart for this one, so we is having that P3 is having. So this is a P3 is given the priority. So first P3 is completing, next P1 is completing, next P1 is completing, and lastly P2. Lastly P2. That is here you are taking the lowest priority first, and lowest numbers 0 to and higher priority 3 to. So 0 lowest priority. So this is a GNAT chart, and if you calculate the average time as per the formula, so P0 for the waiting time for the P0 equal to 0 minus 0, and for P1 11 minus this 11 minus 1, for P2 14 minus 2, and P3 5 minus 3. So adding on and dividing by 4, we will get the average waiting time. So in this one, average time is increasing as if you compare FCFS and shortest job and a priority. In this priority, the average waiting time is increasing. So this is not correct one. So another algorithm is shortest remaining time. So shortest remaining time, SRT is the preemptive version of the SJN algorithm. Shortest job remaining time. So the processor is allocated to the job closest to the completion, but it can become preempted by a newer ready job with shortest time to completion. So impossible to implement in interactive systems where required CPU time is not known. It is often used in batch systems, batch environments where short jobs need to be given preference. So another one is it is most important nowadays multi-programming. We are using this round robin scheduling. In this round robin is the preemptive process scheduling algorithm. Each process is provided a fixed time to execute. It is called a quantum. So as we have seen, this is the program we are writing. So each program in this program, each instruction is a process. In this program, each instruction when it comes for the CPU, that is become a process. This is process 0, process 1, process 2, process 3, like this. So once we know what is the time required for this instruction to be executed, suppose 2 milliseconds. Like this, we know all instructions, what time it takes to execute. We know that. So here, suppose if this instruction is 10 milliseconds, and if this instruction is having the 4 milliseconds and 6 milliseconds and 7 milliseconds, what we do? So suppose this is 10 milliseconds. Till 10 milliseconds, second instruction has to wait for the queue in the queue. So here this waiting time is increasing. So what we do in this with this round robin, we will decide the time quantum. Each instruction how much time equally spent with the CPU. So suppose if you set the quantum 2 milliseconds, so the first instruction will come for the CPU for execution. It will spend 2 milliseconds. After that one, switch over to second instruction. Second instruction also spend with the CPU for 2 milliseconds. So like this, each instruction will spend 2 milliseconds. After completion of 5 instructions, immediately the switch goes to first instruction where it is stopped at where it has stopped earlier. It starts from there onwards. After 2 milliseconds, where it is stopped, the first instruction, it starts from there. It's there onwards. So that is like this. After completion of again 2 milliseconds of the second turnaround, first round, and each instruction will spend 2 milliseconds equally with the CPU. So like this, the complete program will be executed equally. So this is called round robin based on the time quantum. Round robin time quantum. So in this one, this is the nowadays we are using the multi-programming environment. So this is so these processes provided a fixed time to execute. So each process will be provided with the fixed time of execute is called quantum. As per the quantum only, the program execution will be going on in the CPU. So once a process is executed for a given time period, it is preempted and other process executes. So after preemption of the first instruction, after 2 milliseconds, so second process will come and execute for the 2 milliseconds. After that one, again it will be staggered somewhere else and saved somewhere else. And third instruction will be given the same 2 milliseconds. So like this, each process will spend 2 milliseconds with the CPU. So this is once the process executed for a given time period, it is preempted and other process executes for a given time period. Context switch is the used to save states of preempted processes. Context switch is a technique which is shifting from one process to another process after completion of the time stipulated time. So this is a algorithm example. So if you look at this one, quantum, if we set the quantum 3 for the same example, so first P naught will spend for the 3 milliseconds. After P1 will come 3 milliseconds, and P2 will spend 3 milliseconds, and P3 will spend 3 milliseconds. After that, immediately the switch goes to again P naught where it has left. It will continue from there. So this is a round robin algorithm. So if you calculate the wait time for each process in the system, the wait time equal to service time minus arrival time. So here 0 minus 0 wait time, and next here again P naught is coming after 12 milliseconds. So 12 minus arrival time, that is service time minus arrival time. So it is coming after 3. So now 12 minus 3, so 9. This is the total wait time for the P naught. So if you calculate all these things, similarly, you will get in this one average wait time is coming 8 by 5. So multi-level queue scheduling, multi-level queues are not an independent scheduling algorithm. They make use of other existing algorithms to group and schedule jobs with the common characteristics. Multiple queues are maintained for processes with common characteristics. Each queue can have its own scheduling algorithms. Priorities are assigned to each queue. For example, CPU-bound jobs can be scheduled in one queue, and all IO bound jobs are in other queue. So as we see in the queuing of the processes in the RAM. So the process scheduler then alternately selects job from each queue and as per the requirement and assigns them to the CPU based on the algorithm assigned to the queue. So multiple process scheduling. So multiple process scheduling are a multiprocessor scheduling focus on designing that system scheduling function which consists of more than one processor. The multiple CPU share the load in multiprocessor scheduling, so the various processors run simultaneously. In general, multiprocessor scheduling is complex as compared to single process scheduling. In the multiprocessor scheduling, there are many processors and are identical, and we can run any process at any time. So, as you know, in the earlier days, the first microprocessor was 8086. So 8085. 8085. Before this one, 8080. This is a starting microprocessor. After that, 8085 8-bit processor. After that one is 8086 16-bit processor. So now we are getting on the laptops or systems. Earlier we got single processor. Now we got i3, i7, i5, i7 like this. It means that instead of single processor, in the single processor, only one ALU will be there. Now in a multiprocessor, there will be, suppose i3, there will be 3 ALUs at the same, instead of one single processor, we will have 3 ALUs. So this is nothing but instead of one single processor, we got 3 processors. This is what multiprocessor. So suppose this is a program we want to execute, and these are the instructions we have to execute. So some instructions will be allotted to the one processor, some instructions will be allotted to the another processor, some instructions will be allotted to the another processor, because simultaneously all the instructions will be executed by all the processors simultaneously. So these first 2 instructions will be allotted to this processor 1, processor 2, processor 3. Like this, the instruction will be allocated to the different processors in the multiprocessor scheduling. Multiprocessor scheduling. There are many processors and they are identical, and we can run any process at any time. This is our multiprocessor. This is a difference. Earlier we used to have single processor, that is a Pentium or Pentium. So later on, dual processor. Now we have got i3, i7, i5. This is the meaning of this multiprocessor. Instead of one ALU, there will be i5 means 5 ALUs will be there, 5 processes will be there. So whatever program we want to execute, that program will be in that program. The instructions will be allotted to each processor simultaneously. The process will be running independently, but there will be coordination between these processors. If one processor is running by sharing the shared memory, other processors also coordinated or wait till get the IOs. So multiprocessor scheduling. So multiprocessor systems may be heterogeneous, different kinds of CPUs, or homogeneous. So there may be special scheduling constraints such as device connected via private bus or to only one CPU. There is no policy or rule which can be declared as the best scheduling solution to the system with a single processor. Similarly, there are there is no best scheduling solution for a system with multiprocessor as well. So approaches to multiprocessor scheduling. There are two approaches to multiprocessor scheduling in the operating system: symmetric multiprocessing and asymmetric multiprocessing. Symmetric multiprocessing, it is used where each processor is self-scheduling. All processes may be in the common ready queue, or each processor may have its private queue for ready processes. The scheduling proceeds further by having the scheduler for each processor examine the ready queue and selects process execute. So as you know, ready queue is a RAM. Our data will actually program in the hard disk. So the scheduler, the work of schedulers are bringing the what are the program we want to execute from the hard disk to the RAM. RAM is a ready queue. So there may be symmetric and asymmetric. In the symmetric, independent schedulers will be there. As in asymmetric, it is used when all the scheduling decisions and I/O processing are handled by a single processor called the master server. The other processes execute only the user code. This is simple and reduce the need for data sharing, and their entire scenario is called asymmetric multiprocessing. So in the multiprocessor scheduling, and there will be shared data, but processes are running independently. But there must be coordination between one processor to another processor. Suppose one processor using one I/O variables, the other processor cannot use the same variables same time. So there must be coordination between the multiprocessor. That is symmetric multiprocessing. So multiprocessor scheduling, process affinity. So process affinity means a process has an affinity which the processor is given a process or thread to run on for the processor in which it is currently running. So when a processor runs a specific process runs on specific processor, there are certain efforts on the cache memory. So as we know, this is our multiprocessors: processor 1, processor 2, processor 3, and this is our program. This is our program what we are going to execute, and some instruction will be allotted to the process 1, some instruction will be allotted to the processor 2, and process A as it is. So when a process runs in a specific processor, this is one process running in a specific processor. There are certain effects on time and the cache memory. So as you know that there will be cache memory for each microprocessor. So that affects, because one instruction has already here, but another processor want to use this one, then there will be difficulty. The data must recently accessed by the process populate the cache for the processor. So whatever data is being accessed by the processor, it will populate to the cache of the other processor also. As a result, successive memory access by the process is often satisfied in the cache memory, because in the cache memory, as you know, once one instruction is moving from one RAM to CPU. So at the same time, that instruction will also be available in all the three caches. Suppose it is I3, so each processor will have its own cache. So that instruction will be replicated in all the caches, so that whenever that processor want to use this any IO or any data, so that will be easy for that one. As a result, successive memory access by the processor is often satisfied in the cache memory. So no need to go to hard disk or RAM. So types of processor affinity. Soft affinity: when a operating system has a policy keeping processes running on the same processor but not guaranteeing it will do so. This situation is called soft affinity. Hard affinity is also allows a processor to specify a subset processor on which it may run. So there will be load balancing. Load balancing is a phenomena that keeps workload evenly distributed across all processors in a symmetric multiprocessing system. Load balancing is necessary only on systems where each processor has its own private queue of a process that is eligible to execute. So as I know, this is a program, and this is a program. These are the instructions, and these are the multiprocessors, and the one P1, P2, P3, and these are the instructions will be some instruction will be allotted to the some processor, and if more instructions are allotted to the, another second processor, so that will imbalance will be there. So that this program, this scheduling will make sure that there will be load balancing for the processors for doing the execution of the program. So the instructions will be distributed among the processes in equal as per requirement. So multiprocess scheduling, one or more processes will sit idle while other processes have high workload with its list of processes waiting in the queue. So there are two general approaches to load balancing: push migration and pull migration. In push migration, a task routinely checks the load on each processor. If it finds imbalance, it is eventually distribute the load on each processor by moving the process from one overload to the idle or less busy process, as we discussed. So because the instruction will be distributed to the processes equivalently, so that one process should not sit idle and one process will be working. So that is called imbalancing. In that case, there will be push migration, and full migration occurs when an idle processor pulls a waiting queue from a busy processor for its execution. So this is called full migration. So this is a load balancing. So CPU scheduling for real-time operating systems involves special issues. Real-time scheduling has of two types: soft real-time scheduling and hard-time scheduling. In soft real-time scheduling, which doesn't guarantee when a critical real-time process will be scheduled. So in hard real-time scheduling, in which the process must be scheduled before the deadline. That we'll see. So we'll see real-time scheduling and soft real and soft hard in the next class.
Like, share and subscribe. Hit the bell icon for more updates.